What's up, scholars? Today we're talking about relating the factors, zeros, and graph of a polynomial. So let's start out with identifying zeros from a graph. Looking at this example, what are the zeros of the following function? What is that even asking us for? That's the same thing as asking us for the x-intercepts. X-intercepts. Okay, so we've got a 0 here at -3. We've got a 0 here at +1, and we've got a 0 here at +4. Those are the zeros, aka x-intercepts, of the following function. What is the output of a function when you input a 0? What is that even asking? The output of a function, so that's saying what is the y value when you have one of these zeros? What is the y value for all these suckers? Well, it's always equal to 0. Y is always equal to 0. All right, so let's identify the zeros from this function here. If that means that the y value is going to equal 0, let's plug in 0 for what would be y, which in this case is g of x. So we'll replace g of x with 0, 3x to the 4th minus 14x cubed minus 5x squared. And how are we supposed to figure this out? I don't know. I do see we've got a greatest common factor. Let's take that out. They all have an x squared. I could take out an x squared. And now I've got 3x squared minus 14x minus 5. Okay, well this is a trinomial, which I know how to factor with my ACB tree. So let's try to factor this sucker with our ACB tree. A is 3, B is -14, C is -5. So A times C equaling B. A times C is 3 times -5 is -15. So I need two numbers that multiply to be -15 and add to be -14. I could do -15 and +1. That would work. So let's split this middle term at -14x into -15x and +1x. So that x squared in the front that we took out, greatest common factor. 3x squared minus 15x plus x minus 5. So we just split the middle term into the two magic numbers we came up with, tacked on x's here. We'll group our first two terms and our second two terms. 0 equals x squared. Here let's take out 3x. We'll be left with x minus 5. Our greatest common factor here is going to be 1. X minus 5. We know we did a great job because the parts in parentheses are the same. So this becomes x squared times 3x plus 1 times x minus 5. It's factored, but now how do I find the zeros? We remember this from factoring and finding zeros, hopefully. All these terms, all these factors are being multiplied together. So if we're multiplying things together and they're going to equal 0, one of those things has to be 0. The only way to multiply stuff to get 0 is for one of these things to equal 0. So we have three different options. Either this one equals 0, this one equals 0, or this one equals 0. Let's set them all equal to 0, and all of those would give us possible answers to this multiplication problem where we multiply three things to equal 0, and those will be our zeros. How many times do you think I said the word 0 right there? Definitely not 0. Set each factor equal to 0. Set each factor equal to 0 and solve. There we go. So we'll have x squared equals 0. 3x plus 1 equals 0, and x minus 5 equals 0. So this is going to get us x equals 0. We'd square root both sides. Square root of 0 is 0. We would subtract 1 and divide by 3 and get x equals negative 1/3. And add 5 and get x equals 5. Those are our zeros of the function. Zeros happen when the y value is 0. Another name for zeros is x-intercepts. We would have x-intercepts of this function at 0, negative 1/3, and positive 5. Now it is super duper easy to find the zeros of a function if it's already been factored. You're just going to set each of the factors equal to 0 and solve. Set each factor equal to 0 and solve. This is so easy, in fact, that you're going to do the next one. With your big brain, Right now, let's talk about using the zeros of a polynomial to sketch a graph. Okay, so we're going to graph this function, y equals x plus 2 times x minus 1 times x minus 3. So first, let's find the x-intercepts. We'll say graph x-intercepts. Where are the x-intercepts going to be? Well, they're going to be where each of these factors equals 0. So we'll have x plus 2 equals 0, x minus 1 equals 0, x minus 3 equals 0. So we'll have an intercept at negative 2, at positive 1, and at positive 3. So we've got a point at negative 2, positive 1, and positive 3. We can also graph some points in between those intercepts. Graph points in between x-intercepts. So, let's see. I've got an intercept at negative 2 and an intercept at positive 1. I could graph a point in between here if I plug a number for x that's in between negative 2 and positive 1 into my function. The easiest one would be 0. Let's plug in 0 into the function. Y equals, we'll say, we're going to look for where x equals 0. We're going to plug in 0, 0 minus 1, and 0 minus 3. So we're going to get 2 times negative 1 times negative 3. 2 times negative 1 is negative 2 times negative 3 is negative, no, that's positive 6. So we've got a point at 0, 6. 0, 6. Love it. Now we can do another point between these two intercepts, between 1 and 3. That's going to have to be 2. So we'll plug in 2. Y will equal 2 plus 2 times 2 minus 1 times 2 minus 3. Y is going to equal 4 times 1 times negative 1. 4 times 1 is 4 times negative 1 is negative 4. So we've got another point at 2, negative 4. 2, negative 4. And now let's connect the dots. Step 3. Connect the dots with curves. Okay, this is not going to be a pointy thing here. This is not an absolute value function. This is a polynomial graph. It's got smooth curves. So we need to make it from this point up to this point, back down to this point, down to this point, back up to this point. So we're going to look something like this. Whee! Woo! Comme ça. Très bien. Now we could have known the shape from the beginning if we saw that our degree, if we had multiplied this out, the degree would be 3. Right? This would have been a degree 3, so it's odd. And our leading coefficient, there's no other number in here, we assume it's a 1. That's a positive number. Leading coefficient equals 1, so that's positive. So we know from our end behavior discussion that an odd positive has a left side going down, right side going up, just like this graph does. Nice. All right, you're going to do the next one. This is a you-try situation. Do the same steps. Plot your intercepts, plot points between the intercepts, and connect with curves. So same steps, graph the intercepts, graph points between the x-intercepts, and connect your dots with curves on that next example. All right, now let's talk about the multiplicity of a zero, the multiplicity of a zero. So we're going to start with this example. Let f of x equal quantity x plus 1 times quantity x plus 1 times x minus 2 times x minus 3. Find the zeros of this polynomial function. How do we find zeros? Well, we set each factor equal to 0. So we've got x plus 1 equals 0, x plus 1 equals 0, x minus 2 equals 0, and x minus 3 equals 0. If we solve this, we get x equals negative 1, x equals negative 1, x equals positive 2, x equals positive 3. We notice that this 0 here occurs twice. Okay, so we're going to say that has a multiplicity of 2 because it occurs twice. These two zeros only occur once, so they have a multiplicity of 1. Multiplicity. A 0 has a multiplicity in some number if the corresponding factor appears that number of times. So again, this factor here appeared twice, so it would have a multiplicity of 2. These factors appear once, so they have their zeros have multiplicity of 1. So let's write this with an example with some numbers. Let's say f of x equals x minus 5 quantity cubed times x plus 3. We would say this 0, if we set this factor equal to 0 and solved, we'd get x equals 5. That has a multiplicity of 3 because it occurs 3 times, where it would if we wrote it all out. X equals negative, or x equals 5, that 0, x equals 5 has a multiplicity of 3. A multiplicity, whew, that is the word multiplicity. That's this word right here, of 3. Or in an algebraic language here with no numbers, x minus a to the h, the 0 has a multiplicity. I might have a hard time with that word. Multiplicity of h. Whatever the exponent is. So whatever the exponent is on a factor, its corresponding 0 will have that multiplicity. Cool. So let's go from zeros now to a function in standard form. So we've got a 0 at x equals 2, a 0 at x equals 4, a 0 at 0 with a multiplicity of 3. So let's write it in factored form first. That's going to be f of x equals, remember, if our 0 is at 2, then our factor is x minus 2, x minus 2, right? If our 0 here was at negative 1, our factor came from x plus 1. If our 0 was 2, our factor is coming from x minus 2. So we've got a factor at x minus 2, factor at x minus 4, and the factor at x minus 0. Minus 0 is nothing, so we can leave that as just x. But there's 3 of them. There's a whole 3 of them. Good gravy. Well, I could multiply these together easily. I'd call that x cubed times x minus 2 times x minus 4. And then if I'm supposed to write this in standard form, I gotta multiply this whole thing out. Standard form. So we would multiply those two, and then we'll multiply our answer by x cubed. X times x is going to be x squared. X times negative 4 is negative 4x. Negative 2 times x is negative 2x. Negative 2 times negative 4 is positive 8. So this is x squared minus 6x plus 8, all times x cubed. That is a 3 times x cubed. So our standard form, x cubed times x squared is x to the 5th. X cubed times negative 6x is negative 6x to the 4th. And x cubed times 8 is 8x cubed. Okay. Excuse me. So multiplicity means how many times that 0 occurs. Something has a multiplicity of 3, its factor will show up 3 times, aka when you set it equal to 0, the 0 will occur 3 times as well. Alright, let's do another one. Write a function in standard form with the following zeros. X equals negative 3, it's got a multiplicity of 2, so you've got the factor x plus 3 occurring twice. And a 0 at x equals 3 over 4? What? Let's unsolve this. Unsolved mysteries. Excuse me. So let's get this so that it's got something equal to 0. X equals 3 over 4. So if we multiply by 4 on both sides, then we get 4x equals 3, and we subtract 3 on both sides, minus 3, we get 4x minus 3 equals 0, so this must be our factor that came from that 0. It doesn't say anything, so it must have a multiplicity of 1, so this will be 4x minus 3, and then to get this in standard form, this was factored form. To get this in standard form, we got to multiply this all out. I cannot distribute the exponent here because I got a plus in the middle, so I have to write out x plus 3 times x plus 3 times 4x minus 3. So let's multiply 2 together first, and we'll get x squared plus 3x plus 3x plus 9, which will be x squared plus 6x plus 9, and then multiply that by 4x minus 3. I'm going to leave that as an exercise to the reader, and you should get f of x equals 4x cubed plus 21x squared plus 18x minus 27. Blarg. That doesn't look beautiful, but that's what it is. Okay, so again, multiplicity of 2 meant that factor showed up twice. We unsolved this fractional 0 to figure out what its factor must have been. Wrote it out. We could not distribute the squared to each of these parts. We had to multiply x plus 3 times x plus 3, and then multiply by the third term. Okay. We're almost done. You're doing great. Last thing we're going to talk about is how a multiplicity affects a polynomial's graph. If a multiplicity has if a factor has a multiplicity of 1, it's going to go straight through your x-axis. So it'll go straight through. Whee! Okay? It's going to go straight through. If your factor has a multiplicity of 2, it's going to touch the x-axis and bounce off. It'll touch the x-axis and bounce off. Just like that. Okay? If it's got a multiplicity of 3, it's going to touch the x-axis, hang on for a minute, and then come back down. So I'd go touch the x-axis, hang on for a minute, and come through. Okay? Alright. So multiplicity of 1 goes straight through the x-axis. Multiplicity of 2 bounces off the x-axis. Multiplicity of 3, that hangs on to the x-axis and then goes through. So let's look at some graphs and see if we can identify their multiplicities. Okay. We've got, first let's find the zeros. We've got a 0 here and a 0 here. This 0 goes straight through, so it's got a multiplicity of 1. So we had a 0 at -3 with a multiplicity of 1. This 0 here at 1 hangs onto the x-axis and then goes through, so it's got a multiplicity of 3. Multiplicity of 3. That should be the number 3. Great. So again, multiplicity of 1, straight through. Multiplicity of 2, bounces off. Multiplicity of 3, hangs onto the x-axis, and then goes through. You're going to try the next one. We have one more together. You ready? Write a function in factored form. Oh, thank goodness. No standard form action. Factored form, what would be the degree of the function overall? So, let's find our zeros, turn them into factors, figure out their multiplicities, and go from there. So we've got zeros here at -2. X equals -2. This one bounces off. Bing. So it must have a multiplicity of 2. Mult of 2. We've got another 0 here at +1. It goes straight through, so it has a multiplicity of 1. And another 0 here at 3. That also goes straight through, so it's got a multiplicity of 1. So now let's convert these zeros into factors. So this is going to become, these are the zeros. So the factor that goes with it is going to be x plus 2, x minus 1, and x minus 3. So our function is x plus 2 to the second power because of that multiplicity. X minus 1, it's to the first power, so I don't need to say anything fancy. And x minus 3, again, to the first power, so I don't need to say anything fancy. All right, last one is for you. Same idea. Find your zeros, their multiplicities, figure out the corresponding factor that goes with that 0, and write out your function. All right, that is it, scholars. We talked about identifying zeros from a graph, identifying zeros given a function. We talked about using the zeros of a polynomial to sketch a graph. We talked about multiplicities of polynomials, and we even wrote functions based off of graphs using multiplicities and zeros. You guys are great. Love you so much. Keep on that hustle, and I'll see you next time.